All right, this is going to be a really quick rundown on polyprotic acids and bases, their numerous Kas and Kbs, and how you can keep track of all of them. As a reminder, a polyprotic acid is a Bronsted acid that can donate multiple protons, and a polyprotic base is a Bronsted base that can accept multiple protons. And those are pretty much always going to be just the conjugate bases to polyprotic acids. With the exception of sulfuric acid, or H2SO4, polyprotic acids will be weak acids. So as each proton leaves, it will be harder for the next proton to leave as well. For example, say I have carbonic acid, and the first proton leaving looks like this, where carbonic acid and water form bicarbonate and hydronium. Because this is the first proton leaving, we're going to call its equilibrium constant Ka1, and this has a value of 4.3 times 10 to the minus 7. Now we can see here that the conjugate base, bicarbonate or HCO3 minus, also has a proton available to leave. So the second proton leaving is written out as such, with bicarbonate reacting with water to produce carbonate and hydronium. And since this is the second proton leaving, it has an equilibrium constant of Ka2, which is 4.8 times 10 to the minus 11. Comparing these two, it's clear that Ka2 is much smaller than Ka1, making HCO3 minus a much weaker acid than H2CO3. This is the trend we'll always see for polyprotic acids. Acid strength continues to decrease as more protons leave. Now let's think about polyprotic bases. Remember what I said earlier about polyprotic bases just being the conjugate bases of polyprotic acids. So for these two acids, their conjugate bases are highlighted here. Carbonate is the conjugate base to bicarbonate, and bicarbonate is the conjugate base to carbonic acid. The base equilibria for these two look like this, where bicarbonate and water react to form carbonic acid hydroxide, and carbonate and water produce bicarbonate and hydroxide. So because these are base equilibria, they should each have an associated Kb, but how should we number these? Just like before, where Ka1 corresponded to the first proton leaving, now Kb1 will go with the equilibrium for the first proton being added to the fully deprotonated base. And in this example, that's the reaction with carbonate. And Kb2 will belong to the second proton being added. So that's the one that I have written up here of HCO3 minus reacting with water. So even though the acid equilibrium with carbonic acid goes with Ka1, the base equilibrium producing carbonic acid has Kb2. Students often get confused by this with the numbers flipping and all, but I think it helps to just emphasize what the letters and numbers mean. In acids, we're counting which proton is leaving, starting from the fully protonated acid. And in bases, we're counting which proton is being added, starting from the fully deprotonated base.